This is a sample problem from another book. But what's going on here is we have this mass on a spring here and the string there. It's all attached to one thing, and the mass is going down the hill, okay, indicated by the red arrow. So it's going to be traveling 20 centimeters along the hypotenuse here, and the spring constant is 100 newtons per meter. And it's a rough surface, so what you need to do is find the coefficient of kinetic friction. So anytime it's rough, it's going to be the work done by friction equal to the other energy terms, the change in kinetic energy, change in gravitational potential energy, change in spring potential energy. It's always that. Anytime you have a rough surface, so it's going to be stuff, work done by friction, negative mu k, equals the other stuff, change in kinetic energy, change in potential, gravitational potential, and gravitational spring potential. Okay. Any questions on the setup before I break you up? Yeah, it's from the other book that had a lot of good examples on energy. No questions, so let's see if we can get the correct answer here.
Mr. Kelly.
Yeah.
So after 20 centimeters, it stops?
Yeah, after 20 meters, yeah, it comes to rest. So yeah, so it's so exactly. So yeah, keep it down. So 20 centimeters. It doesn't necessarily get to the edge of the ramp, but it just travels 20 centimeters. So that's all that's important. Okay. Okay, so HI needs to be found now. HF is equal to 0 here. We have a difference in gravitational potential energy. We also have a difference in the spring potential energy, because once the block starts moving, it's going to stretch it from 0 to some final position. That final position here is going to be the distance traveled down the ramp, which is 20 centimeters or 0.2 meters. So let's get consistent here. So far, so good. It's a rough surface, so we set the work done by friction equal to all of the other energy terms: kinetic energy, potential, gravitational potential, and spring potential. And that's what we do for all of these problems, whether it's on a ramp like this or whether it got a spring, on the bottom, or whatever configuration it is. If you have a rough surface, work done by friction equals other stuff. And it's up to you to establish, especially with the gravitational potential, to establish the positions. You can establish 0 to be anywhere. It could be here, it could be bottom. And there's a ramp. So we have a right triangle action forming here. So we can find our height by using trig. This angle in here is also 37, similar triangles, and the problem's fairly easy after that. At least I hope. We'll dissect it now. Okay. So work done by friction is going to be equal to change in kinetic energy plus change in gravitational energy plus a change in spring energy. Since it starts and stops at rest, the change in kinetic energy is 0. Now, if the problem said it's still moving after 20 centimeters, then we'd have this final kinetic energy term, where the initial kinetic energy term would be 0, but the final kinetic energy term would not be, because the stipulation would be the problem, or the block is still moving. But since it starts and stops from rest, and ends at rest, delta K is 0. And so the work done by friction, kinetic friction here is going to be UK Fn delta X, which is going to be equal to change in gravitational energy plus change in spring. So we have everything. Mu K is the final goal. We have to get this Fn. We know what delta X is. Delta X is going to be 0.2 meters, 20 centimeters. We can easily get the initial gravitational potential energy. This term becomes PE final minus PE initial gravitational plus 1/2 K delta X final and we know that this term is equal to 0. The displacement in the final case is going to be final minus initial from where it was. Final is 20 minus initial is 0. So this is our term that's left. Since there's no displacement at all in the beginning, this initial term goes away. The final gravitational potential energy is equal to 0 because our reference level will be 0 there. That means at 0 that there is no height. We know that gravitational potential energy is equal to mgh. And since the final point here is height 0, there is no final potential energy, the gravitational potential. So let's expand this even more. Now this Fn, okay, we have to figure out how we're going to get this normal force. How will we get the normal force here? What's that going to be equal to?
mj cosine theta.
So we have to do a free body diagram on the box. And to get our Fn, so like, we just do it as we've done before. So here's Fn, and then mg is always pointing straight to the center of the Earth. This is going to be mg cosine theta. And then this was mg sine theta. So Sam, you're correct. So normal force will be equal to mg cosine theta. Fn minus mg cosine theta equals 0. Set them equal. That's what the height's going to be. Well, that's what Fn is going to be. And so as we continue to dissect this guy, so no longer Fn, but mg cosine theta, 37 degrees, times delta x. Delta x is 0.2. All right. Then we have to get the height of the block. So we have to get this guy. So we have a right triangle situation here. So we have like this H final, H initial, that's, well, actually it's not, it's going to be the other way around because we're going from top to bottom. So he's 0. So we can get We can get this initial height here by doing trig. So this is the height's going to be, you know, sine of this angle multiplied by 0.2. Okay, so again, so sine of 37 is going to be the opposite, which is what we're trying to find over the hypotenuse. And so the h that we're looking for, 0.2 times sine of 37. And so it's going to be 0 minus mgh, which is, this is the h, 0.2 sine of 37. So that's going to be an all one big block there, because we have final gravitational potential energy minus initial gravitational potential energy. And that's going to be a negative because we're going from a high value all the way down to 0. So we're losing potential energy, gaining kinetic energy, but at this point it comes to rest. So the kinetic energy at that point, it will be 0. But this is how much potential energy you have in the system. It's going to be lost because 0 minus anything is going to be negative. And then, so we have 1/2 the k delta x squared, where the k value is 100 and delta x is 0.2. So let's put everything together, put our numbers in, and we should get mu k now. So the mass is 2 and then minus divide that by the other stuff here. 2 do that and multiply by 0.2. And once you work that all out, you should get like 0.115. I mean, we can do the math and all that, but you know, I'll save that step for you. We all get that, or any questions on any point here?
Yeah, what was the -1/2 times 100 times 0.24 again, squared?
That's the spring energy, 1/2 k x squared.
Okay.
Yeah. So this should, you know, all be negative divided by, and the negatives cancel out, so it becomes positive. So yep, 0.115. So again, just to summarize these type of problems, if it's a rough surface, in this case, it started and stopped at rest. We set the work done by friction equal to all the other energy terms. If it was frictionless, no rough surface, then this would be 0 equals this stuff. That's it. That's pretty much the style of conservation of energy problems. And there's that. Okay, so let's go back up to momentum. chapter 9. So last time we were talking about collisions. I'll do a rederivation of the conservation of momentum, then get to the, some sample problems for us to do. Let's do that. And then that'll be our day. All right. So I'm going to talk about impulse momentum. You can go over your notes on that. So I'm going to be specifically at end of section 9.1 and into 9.3. But we will see an impulse problem, graphically speaking, that is. Okay, so see, I'm gonna do this here. So let's say we have two objects that hit each other in an elastic collision. So they had an initial momentum before the collision, and then they had a final momentum, both of them after the collision. So we saw that last time. So we had object number one. This will be the initial condition. They hit, collide, fire, and then they go backwards. We've already talked about impulse, that the impulse that both of these objects exert on each other is going to be equal and opposite. F delta T, 1 on 2 is going to be minus F delta T of, this thing here. 2 on 1, this is object 2, object 1. Okay, so they hit at the point of collision. These impulses happen, they're equal and opposite, and then they go away. They rebound and go the opposite directions. We know that F delta T for each one of them is going to be equal to a change of momentum for both. So both of these objects change each object's momentum respectively. So this is object number 1 on 2, or we could specifically, just in terms of the context of what I want to derive right now, is just to take away that. This is object number 1 and object number 2, equal and opposite impulses. So we know that F delta T 1 is going to be equal to M1 delta V1, because its momentum is being changed by object number 2. And then likewise, F delta T here is going to be equal to negative M2 delta V2. And so last time, we were trying to get this relationship between the changes of momentum for both objects. We have object number 1's momentum, the change of momentum of object number 1 equal and opposite the change of momentum of object number 2. Let's see what we can do with that. Can we simplify it? And as we did, we found a new relationship between the two masses. Specifically speaking here, this should just be delta T, because the time of collision is going to be the same. So this is 1 on 2, 2 on 1, and that's a little bit more exact, a little bit more specific there. Okay, so we set the change of momentum of object number 1, M1 delta V1 here. And we stretch it out because we know that delta of anything is going to be final minus initial. So we have M1 V1 final, V1 initial. And so at this point, We combine like terms, the initial terms on one side, and final terms on the other. But before I do that, let me just factor this out a little bit more. All right. So finals on one and initials on the other. So we have this. So what we're saying here is that the momentum of both objects in the beginning is equal to the momentum of both objects in the end. The momentum doesn't change. The only thing that matters in this situation can only exist if the forces in the system are the forces between both objects. It can't be any outside forces like force of friction or somebody pushing one of the masses or both of the masses. So the only forces are the collisions in between both masses. The same amount of time, obviously. Those respective impulses change each object's momentum respectively. And so here, we just simplify things out. And we get this relationship that the momentum in the beginning is the momentum in the end. The sum of all momentum in the beginning, because I say sum because it can be 2 objects or 10 objects or however many. You can say pi equals pf or sigma, you know, same thing. So easy language here. Objects is equal to momentum, or momenta, yes, you know. Momentum is saved or conserved, whichever you wish to say. It's the same thing. So no change in the momentum. The momentum is conserved. Conservation of momentum equation laid out here. Okay. Yeah, for just normal momentum, P is equal to, that's the symbol for momentum, sorry. Where P is equal to mv, yeah. And so they hit each other, both momentums get m delta v'd, and then we get this relationship. So that's for general elastic collisions. So we have the inelastic collisions. We're talking about last time that in an elastic collision, momentum and kinetic energy are saved. But in perfectly inelastic collisions, only the momentum is saved and some of that energy is lost to deforming the objects, to heat, to sound, to whatever else. And we showed in one problem that the momentum is actually saved, but we didn't do the next part where kinetic energy is not saved. So we'll do a little bit of that today. So again, just to repeat here, elastic collisions, momentum, and kinetic energy are saved. So we have those equations, we'll write them down as we get to them. Perfectly inelastic collisions, those are collisions where two or more objects hit and they stick together. Inelastic, there's no rebound. Elastic implies a rebounding effect or bouncing off. Okay, so momentum. That's what I gave that one, problem number 16 is to get you to see that the kinetic energy is not saved. Some of it's lost. Okay, momentum is saved, but kinetic energy is not. So the conservation of momentum equation is really like the elastic equation, same. So for elastic collisions again, so for two objects, that's the momentum saved, and then kinetic energy. And so let's see if we can get a problem where we can prove that either today or next time. All right. I'm gonna say the PE for short, or PI. So in the beginning, so both the objects don't have to be together. One of them can be at rest, it doesn't matter. Even in the elastic case too. So both masses hit, stick together, and move at one common speed. Yeah, so that's what we have for the perfectly inelastic momentum case. The P momentum and kinetic energy, not the same. So let me just break you out yet again on the impulse question. So what we're going to look at now, look at impulse question for like 5 minutes. Come back, let's do some momentum stuff. So what I want to do now is direct your attention to chapter 9. Question 7. So we're going to do, so we're looking at page 261, number 7. So we have an estimated force time curve for a baseball struck by a bat as shown in figure 9.7. From this curve, determine the impulse delivered to the ball, the average force exerted on the ball, and the peak force exerted on the ball. So anytime that we have a multiplication like impulse, force times time, that results in impulse, that multiplication is an area. So we do the area under the curve or area under the function to get the impulse in this case. If it was get the work, it'd be force versus delta x. And then we do the area underneath that curve to get the work, sort of thing. So remember, impulse is equal to force times time. This is a force time curve. Area underneath to give you the impulse. That should give you the letter A. And as we've stated, that equals to a change in momentum, which is m delta v, which is, all those are equal, same thing. So yeah, the peak force there, 18,000. I just gave you letter C. So yeah, that's the, so let me just let you go and do that for a couple of minutes. Any questions, comments? All right. So give some time to do that. So like, give you about 5 minutes or so. Maybe like 7 minutes. All right, see you when you get back. Let's see. You need a partner. Okay, there we go. So Leo, I got to get you. Yeah, you just joined back in. Get you to room number 1. So Selena, you want to join? Sends room. Selena, you here? Selena. Okay. All right, let's talk about this problem. So we are number 7. And they want us to find the average. Let's see. Find the impulse delivered. So again, impulse going to be the integral of f delta t, but we're not going to do this in that style. We're just going to do f delta t, which is the area under curve. And so we can break this thing up into 2 right triangles as an example, right? And so, and then when we do that, so I'm just going to split it. So draw arbitrary deal here. 20K. So this is so okay. So try to get it there. Okay, so we can do this. So we can, right triangles and we just double it. So this splits at 1.5, and this is going to be in terms of milliseconds, so 10 to the minus 3 seconds. So this is going to be like the 1.5 mark. And this height is 18,000. So the impulse is just going to be 18,000 peak there. And multiplied by 1.5 times 10 to the minus 3, all of that, and you double it because it's 2 of the same triangles. So what'd you get for that? Check your answers in the back and make sure you got it right. Did you get 13.5 when you did all that? The impulse being 13.5 Newton seconds. Let me just write this up again. No one got that, or?
Mr. Kelly, is it times 2 or divided by 2?
No, it's multiplied because it's impulse. It's force times time.
I divided it.
You divided it and get 13.5?
Yeah, I divided it because of the area of the triangle. Height times base.
Oh, I'm sorry. I did. Yeah, 1/2. I should do 1/2 here. My bad on that. Absolutely. I'm looking at it explicitly. Multiplication, double. Yeah, 1/2 base times height. Yeah. Apologies for that. So you do this first for this triangle, and then double that. It's awfully quiet today, but that's every day. Yeah, so that's going to be 13.5. So, and Joe, and so not to misspeak on that, impulse is average force times time. So when we do this, we have actually calculated with respect to the average force being what we're going to find next. But this whole operation is the impulse. So that will give us the result, 13.5. So 1/2 base times height. Okay, so then the average force is just going to be this impulse, which comes out to be 13.5 Newton seconds. Average force is going to be impulse divided by time. It comes out to be 13.5 divided by 1.5 times 10 to the minus 3 Newton seconds over seconds, and comes newtons. It comes like 9,000 is our average force. Yeah. You guys get that? Or any questions on how to get that? The peak force, pretty much given in the picture. The maximum or peak force is 18,000 newtons. The average is half of that, which we've calculated there. So again, it's all about contextually, all about the average force times time to get the impulse. If we were doing it in a realistic sense, we'd do the area under the entire function to get the total force exhibited throughout the entire time frame. But our context is average force. and which we got here for part B. And then for part A, for impulse, it's just 1/2 of one of the triangles, 1/2 base times height. And that's what we get there. Any questions? The impulse problem. So the peak force, as I mentioned, is given in the problem in the graphs, 18,000 newtons. Okay. Yeah, we have a little bit of time. That's why I wanted to do one of the collision problems there. So I gave you 16 and 24, right? No time remaining. I guess we can stay here and do this part. So yeah, I want to go back to number 15. We did this in class before Thanksgiving there, and we wanted to calculate the original speed of the bullet, the VI, and then I think Joy, you asked how's the momentum saved. So we got the VI and we set them equal the equations, and we saw that it came out to like 3.006 on both sides, if you recall that. So now it's combined. So what we want to do, I'm going to go back to number 15, page 261. And let's see, we got the original speed of the bullet. Just find that guy here. Yep, and then all that, and then that. 300.6, and then okay. So we got this guy. And so what I want you to do now, some time remaining, is to show how much energy, show that the energy is actually lost from both sides. And so we know that we can do that by initial kinetic energy of object one. And we know it's going to be Ke of both. So basically we have 1/2 m1 v1 initial squared and if we take object 2 to be the target, the block of wood, and obviously the bullet is object 1, let's prove that the energies are not equal. So this already goes away, so that helps you out. And the final kinetic energy, 0.6, and so we know that bullet, the speed of the bullet is this guy, 300.6, and go ahead and show that they're not equal. And there's another proof to yourself that in perfectly inelastic collisions, the kinetic energy is not equal, not the same on both sides. So perfectly inelastic. Hitting stick. And likewise, in an elastic collision, we can show that they are equal. Easy, everybody get that? So hopefully this is rather rudimentary. We can see, all right, our premise has already been established for the most part with energy conservation, momentum conservation. Okay, face value, can we prove it? Yes, we can put all the terms together and show that the momentum is actually saved. All right, it's proved now that the kinetic energy is not the same in the perfectly inelastic collision. Sure, and then we can go and prove that the kinetic energy is equal for the elastic collision case, if we want to. Hmm. Okay. All right, so we have 1/2 the mass of the bullet, which is 10 grams. Let's get that mixed up there. 1, 2, 3. Okay, and then the initial speed, which we found to be 300.6 squared. Let's show that it's not equal to both of these guys. And the block of wood was 5 kilograms. And the speed after 0.6. So this is 451 joules. And we're trying to compare the energies. Man. Carried away on my non-cursive cursive here. Okay, so this is a 5 plus 0.01 times 0.5. Obviously, very much not equal. And then on this side, 0.9 joules. Okay, so that's just another easy proof that the kinetic energies are not equal and perfectly inelastic. And last time we showed that the momentum is equal. All right, any last bits, questions, comments? I'll be here at 2:30. Anybody wants to show up for any additional questions or homework or skills tests I want to keep to Wednesday mornings. But stop on by if you have any questions about anything else. Let's see. Yeah, we'll have one Thursday, but on Wednesday, I'll give you a sample problem. That's going to be similar. So yeah, Thursday is a skills test. Skip the last time.